In this video, I'm going to walk you through the 4 problems that are in the hypothesis testing with 2 samples Excel exercise. To start, you will need to go and make sure that you have the data analysis tool pack loaded up. So if you go up to the upper Excel menu up here and go to Tools, you will see under Tools you have Excel add-ins. And if you click on that, you probably don't have Save as Adobe. You probably have, well, you should have Analysis Tool Pack and probably Solver add-in. You want to make sure that that Analysis Tool Pack is checked. So check that, click OK. And now if you're down in the lower Excel menu and you go to Data, you should see over here on the far right side data analysis. Okay, that's what you just did. You basically added that in there. These are a lot of add-ins for Excel are infrequently used, so rather than sort of clog up the standard Excel program, they put them in as add-ins. So so long as you don't go in there and uninstall that, you should have that going forward. So we have that in there. The first problem that we have here, we have data from 2 cities on hotel room rates. So in this problem you are asked, based upon the sample data, can you conclude that the mean price of a hotel room in Atlanta is lower than the mean price in Houston? So if you write this out as a claim, your claim might be the mean price of a hotel room in Atlanta is less than the mean price in Houston. Okay, so that would make that a one-tailed test. So what we're going to do is we have our data here. Now, you are also told that you know from having a lot of additional data, you know what the standard deviation is for hotel room prices in both Atlanta and Houston. Now, given that you know what those standard deviations are, you're going to be using a variation of a z-test. So what we're going to do is we go over here to data analysis, and if you look at what it gives us here, it gives us a whole slew of different types of tests that you can run here. So I'm going to scroll up here. We've got ANOVA, which stands for Analysis of Variance, various types of ANOVA tests, descriptive statistics, F-tests for 2 samples for variance, random number generation, regression analysis. We're going to be doing that in the last module. T-test, so here we get into some T-tests, paired 2 sample for means, T-test 2 sample assuming equal variance, T-test 2 sample assuming unequal variance. So these are very similar, equal variance versus unequal variance. And here we have a z-test 2 sample for means, and that's the one that we want for problem number 1. So if we click on that, it asks for variable 1 range, variable 2 range. So variable 1, we're going to make that Atlanta, so we'll just click on that and drag it down, and you want to select that range there. Now notice when I did this, I selected the title Atlanta there, and then we click here, variable 2 range. This is going to be Houston, so we're going to select Houston and go all the way down. And notice here that we have a different number of observations for each of these, and that's perfectly fine. Hypothesized mean difference. For all of these problems, it's going to be 0. The null hypothesis is that there is no difference between the mean room rate in Atlanta and in Houston. Okay, variable 1, so that was Atlanta. What is its variance? Now notice here it's asking for variance. It's not asking for standard deviation. So the variance in the standard deviation in Atlanta is $20, so the variance is 20 times 20, or that's 400. Let's see if you can actually do 20 squared, see if it allows that. No, it probably doesn't, so that's 400, so you have to do that calculation. The variance for Houston, you're told that the standard deviation is 25, and 25 squared is 625, so you have those in there. Now, this little box here, labels, since we selected, the range we selected up here included the labels, you want to check the box for labels, okay? If you did not select the labels, then uncheck that box, okay? And we have the option of either putting the output on this sheet, we can specify the range, a new worksheet ply, or a new workbook. So we're just going to put this on the same sheet. We're just going to select an area you just have to give it one cell, and it'll treat that as the upper leftmost cell of where it's going to put it. Okay, so we have all that. Then we just click OK, and here is our results. So it does the hypothesis testing for you. These are the sample means for Atlanta and Houston. Notice here that the Atlanta mean is lower. So the claim that we're looking at, the mean price of a hotel room in Atlanta is lower than the mean price in Houston. That's actually what we have here. The question is it significantly lower? Okay. And so in looking at this, we see that it's lower. We come down here, make sure that your hypothesized mean difference is 0. Here is your test statistic. It is a z. It's minus 1.8. And then it calculates p-values and also critical values. And we're just going to be focusing on the p-values here. So the p-value for a one-tailed test and a p-value for a two-tailed test. Now, our claim, again, was that the mean price of a hotel room in Atlanta is lower than the mean price in Houston. That does not contain an equal sign, so that becomes our alternative hypothesis. The null hypothesis is that the mean price of a hotel room in Atlanta is greater than or equal to the mean price in Houston. Okay, so it's a one-tailed test, so you just need to look at the p-value, and it says here p, z less than or equal to z. One tail, and our p-value here is 0.0352, and we are using a 0.05, alpha equals 0.05 significance level, so that is below that. So you would reject the null hypothesis in favor of the alternative hypothesis, which is our claim, which is that Atlanta has a lower mean price for rooms. Okay. Problem number 2. Here we have SAT math scores based on parents' education. So these are the SAT scores for students split out by whether the parents had college education or high school education. So on this problem, it says a research hypothesis was that students whose parents had attained a higher level of education would on average score higher on the SAT. Okay, so you can sort of write that out as the claim. Notice that this is going to give us a one-tailed test. Okay, so on this one, we don't have an estimate of the population standard deviation or population variance. Okay, so this is not going to be a z-test. It is a two-sample test. It's going to be a two-sample t-test. Okay, so on this one, we go over to data analysis over here on the under data analysis, and we want a t-test. On this one, we're going to be using a t-test assuming unequal variances, and click OK. Click OK. And this gives us something similar to what we saw with the z-test, two-sample z-test. Variable 1 range, that's going to be for college. Parents had college education. Variable 2 going to be for the high school data. Parents had a high school education. Hypothesized mean difference, again, always 0 on these tests. Labels, because we selected college and high school in that thing up there. One thing I didn't mention before, here you can actually specify the alpha level. Okay, so on this one, do I specify, is this specified? Yes, 0.05. So if you put that in, 0.05, that is going to determine what the critical value is that it gives you. Okay, output range, and we're going to again just sort of select a cell to the right of our data. Nothing else is in this area where it's going to go, and click OK. And this is what we get. So here we have students whose parents had a college education had an average or mean, sample mean SAT math score of 538, almost 539, whereas those with parents with a high school education had an SAT math score of 481. So that is consistent with the alternative hypothesis. Is it significantly different? We go down and look at this. This is a one-tailed test. And I should note here, for these one-tailed tests, you always need to make sure that the data up here is consistent with the alternative hypothesis. If these were flipped around, you could just stop there. It doesn't matter what it says down here. If Excel thinks you're doing a say a left tail test and it's actually a right tail test, then you can get the wrong answer going off of the p-value. So always check and make sure that your actual sample data is consistent with the alternative hypothesis, and then ask yourself, is it significantly different? And for that, you go and look at the p-value. So this is a one-tailed test, so p one-tailed test. Now this is in scientific notation, so 2.1384 e to the minus 5. You can move this decimal places, 5 places to the left. Let's see if we can actually change the format here. So let's just change the number format. So you can also change the number format. That's what it looks like and how you typically see it. Okay, so if you're not used to this e to the minus 0.5 stuff, you can always do that. But pay attention for whether there's an e to the something there at the end. Okay, scientific notation. So this is significantly less than 0.05. So again, we would reject the null hypothesis in favor of the alternative hypothesis, which is what our claim was. Problem number 3, we're looking at mean minutes late, or minutes late for a random selection of late flights. So these are essentially filtered. They have to be late to be included or to be sampled, and these are the ones that are sampled. We have 2 airlines, AirTrans and Southwest. And the data looks like the minutes late follows a normal distribution. The reason that's important is because we have sample size is less than 30. We need the population to look normally distributed because we cannot invoke the central limit theorem because our sample size is too small. Questions to answer here. Number 5, formulate the hypotheses that can be used to test the claim that the mean minutes late is the same. Okay, so that's going to involve an equal sign for delayed flights on AirTrans, Airways, and Southwest Airlines. So that's going to make this a two-tail test. And we're going to, it says up here, assume that both populations, let's see, appear to be normally distributed. And this is going to be the same test as what we did in the prior one. So we go up here, let's see, data analysis. And Excel remembers what you last did with this data analysis unless you shut down Excel. So we have t-test, 2 sample assuming unequal variances. Click OK. It remembers what you had the prior time, but that actually doesn't match up with where this data is. So make sure you go in there and select where the data actually is. Hypothesized mean difference is still 0. Labels, check that box. And we are using a 0.05 significance level, so we have that. And then output range, that's okay. And click OK. And so this is what you should get. So it gives you the sample mean. So AirTrans mean minutes lates was 50.6 minutes. Southwest 52.8. So they're not the same. Question is, are they significantly different? And for that, we come down. This is a two-tailed test. And so go down, there's our p-value for the two-tailed test, and it's rather high. It's nowhere near 0.05, quite a bit above 0.05. So with that, you would fail to reject the null hypothesis. Essentially, there's not enough statistical support to say that one airline has a higher mean than the other one. Now, maybe if they went and had a lot more data, you would get something different. But you know, given what we have here, you cannot reach a conclusion that one is more late than the other. On these critical values that they show here, this is derived based upon the fact that this follows a t-distribution with 43 degrees of freedom. Degrees of freedom is calculated for you. And the significance level is 0.05. If we went back in there and changed the significance level to 0.1, the p-values would stay the same, but the critical values would differ. And you can see here that our t-stat is minus 0.316, and the critical value is 2.016. It's actually plus or minus 2.016. So we would either need this to be the t-statistic to be less than minus 2.017 or greater than 2.017 in order to reject the null hypothesis. Okay, finally, problem number 4. So problem number 4, here we have, what do we have here? 20 golfers, and we have, for each of the golfers, we have their first round score and we have their final round score. And the question is, do the averages on the first round differ from their averages on the second round? Now, you could go in there and sort of say, well, ignore that the first round scores and the final round scores come from essentially the same pair of golfers, or the same golfers. But you would end up with a much weaker statistical test doing that. So instead what we do is we basically treat these as being matched pairs, okay? And I'm going to show you 2 ways to do this, okay? I'm going to go through the way that I'm asking you to do it in the assignment first, and then I'll show you another way to do this, okay? That basically makes it into a one-sample t-test, okay? So on this one, let's see. Yeah, so the claim you are addressing is that the mean scores do not change, so they're essentially the same. They're not higher or lower on the final round, so that's going to make this into a two-tailed test. We go to data and data analysis, and we have a t-test paired to sample for means. So that's the one that we want. Click OK. Variable 1 range is going to be the first round. Variable 2 range is the final round. Make sure you check the box that says labels. Hypothesized mean difference, 0. Always 0. Do not go in there and calculate the sample averages and put that in as the hypothesized mean difference. That's not what this is asking for. The significance level, we're using 0.10, so we'll enter that in there. We have the labels box checked, output range this, actually I'm going to stick this farther over here. Okay, then hit OK. And so this is what we have. And the first round and the final round means are fairly similar, 69.65 versus 70.7. We're just looking to see whether the scores changed, the mean changed between rounds. And makes that into a two-tailed test. And we come down here, two-tailed test. And this is where getting whether it's a two-tailed test or one-tailed correct is important. As a two-tailed test, p-value is 0.173. So that's greater than 0.1. You'd fail to reject the null hypothesis if you incorrectly assumed that it was a one-tailed test. So if you said, so suppose your claim was that the pressure of the final round causes scores to go up, to increase, and that's what you were testing, then that would make that into a one-tailed test, and then you would use the p-value of 0.0865, and in that case, that is less than 0.1, and you would reject the null hypothesis. Okay. On the other hand, if you said that your claim was that the competitive spirit really kicks in on the final round and scores fall, your data doesn't support that. Okay. Averages on the final round were actually higher. Okay. So it doesn't matter what the p-values down here would be. Okay. So that's how you do that one. And another way to do this, so suppose we went in here and said, let's look at how the scores change final round versus the first round. So we just take the differences there. So Michael Letzig, his score went up by 2. We just do that, and we can actually go in here and put that in as that's what the change is. If you go to data and data analysis, Excel doesn't actually have a one sample test for, it doesn't have like just a straight t-test here. Let's see. So let's do this by hand. So this is, so let's calculate equals average, get the average. There's the average. Let's get the standard deviation. STDEV dot sample standard deviation. That is that guy right there. Our hypothesized change is 0. And we have n is equal to, we have 25 minus 5, so we have 20. So our t-test, or t-statistic, equals, come over here, it's going to be basically this 1.05 minus 0 divided by the sample standard deviation divided by the square root of the sample size, which was 20, so 20 raised to the 0.5 power, and there is our test statistic. And notice here 1.415989 matches up with what we have right over here. And so if we did this up as a two-tailed test, so if we went equals t test, actually let me do t distribution, two-tail, x degrees of freedom, so n minus 1, so 19, and we end up with, there's our 0.173, and that matches up with that right there. So that's another way to do it, showing you that we could actually have folded this problem into how we would have done stuff in module number 4. Anyway, hope that helps with both Module 4 material and Module 5 material. See you next time.